Okay, now for this again. Here, a basic set of Laplace transforms. All these are easy to derive. I'm going to derive this one for you shortly, and it's actually easier than a lot of these. And since you did really well with the homework, you know how to integrate and get these. Okay, but some of the patterns that you have, like for example, Laplace transform of t to the n, that's a small n there, but hopefully you can read it, is n factorial over s to the n plus 1. Okay? If n happens to be 0, what happens? You get the Laplace transform of 1, which is just 1 factorial over s to the 0 plus 1. Okay? See what I mean? Brain fog. If n is 0, it's 0 here, you get an s here. In other words, if n is 0, this reduces to this. Now this is the first one we looked at. It's extremely easy to derive. The one for just plain old t is easy enough to derive. For t squared, well, we looked at that last time. You begin to see how this builds up and what happens every time you add a t. There's another interesting transformation, incidentally, which would be the Laplace transform of t, f of t. And we're not going to derive this one, but we're probably going to look at it later. This is a little more complicated, just conceptually. Okay. Anyhow, there's one pattern. If n happens to be 0, this reduces to this. Now, if you go to e to the at, notice, and we're not going to talk too much about why this is, although you can look at it geometrically, and it's worth kind of trying to do that, but the Laplace transform of e to the at is 1 over s minus a. It's a lot like 1 over s, isn't it? But you got that minus a in there. What does that have to do with anything? Well, still, it's important to kind of know how to do that integral, which is quite easy. Your e to the negative ts, if you multiply by e to the at, becomes e to the negative t times the quantity s minus a. When you integrate, you're going to get a 1 over s minus a. And, you know, then you got to do the limits and stuff, but that's really easy. So that happens, but still, geometrically and so forth, why is it that the Laplace transform of e to the at has such a similarity to the Laplace transform of just 1? Okay, worth thinking about. Okay, the one that I derived and keep deriving wrong, getting a negative sign here because I'm making a negative sign error someplace. There are two integrations by parts and just some negative signs to multiply, and I don't seem to be able to do that right now. If I didn't skip steps, I'd have at least a chance of getting it right, but I can't bring myself not to skip steps. It's a strange thing. Laplace transform of the cosine of kt is this, and you get an s here. Laplace transform of the sine of kt is this, and you don't get an s here. Okay, you get a k. Why is that? Well, if you look at the integrals, you see where the s appears in the cosine of kt, and it just comes out to the limits of cosine of kt when t equals 0, okay, versus the way the sine acts when t equals 0. And you see where that arises, and it's worth doing that. It kind of locks in these comparisons. Again, if you have enough presence of mind to kind of remember that. And I think right now you'd be better at that than I am. Okay. Then you have this hyperbolic sine and hyperbolic cosine. Now in calculus, you know, I think, why do you call that a hyperbolic sine? Why do you call that a hyperbolic cosine? When I first saw that in first semester calculus, it seemed kind of strange to call it that. I mean, I could see that there are some analogies. This is an odd function just like this is. This is an even function just like this is. And the derivatives act sort of similar, except that, you know, the derivative of the sine is the cosine. The derivative of the hyperbolic sine is a hyperbolic cosine. The derivative of the cosine is the negative of the sine. the derivative of the hyperbolic cosine is the sine. It's not the negative of the sine. So there's one area where it's kind of similar but not exactly the same. But when you get to Laplace transforms, you see that these two transforms for the hyperbolic sine and hyperbolic cosine are so similar to these transforms for the sine and the cosine. Well, there's one hint of a deep connection between hyperbolic sine and cosine and the sine and cosine. Okay, so those patterns are kind of worth being aware of. Now with that, let's go ahead and derive this one. I think I can do this one right because it's really simple. Okay, the Laplace transform of f prime of t, and incidentally, the big deal with Laplace transforms is you can use them to solve differential equations that you can't solve using other methods. Okay, there are a lot of functions even with constant coefficient equations, and they're particularly nice with constant coefficient equations. There are equations you can't solve. Now, just the way you can't solve y double prime plus y equals tangent of x using undetermined coefficients, even though you can do it with variation of parameters, shows you that there are non-homogeneous parts to these equations that can be really difficult to solve. If, for example, you have a circuit, and the circuit is set up so that you have a sine function, some sine function that acts for between t equals 1 and t equals 3 and then stops, you're not going to be able to do that using any of the techniques that you have. And of course, in circuitry, when you're dealing with bits and stuff like that, not so much with a sine, but with a step function. And we'll see that very shortly, probably today. And if not, then next time. Your techniques from higher order equations aren't going to apply at all. Okay, well, that's why we do Laplace transforms, one of the reasons. And there are other reasons, but I haven't dealt that much with Laplace transforms beyond the level of what we do here. I'm aware of some of them, but I'm certainly not a technical expert on that. And these days I'm not a technical expert on much of anything. So, okay, well, allergy season will pass. I'll get a little better. Laplace transform of f prime of t. Again, this is going to be important because this is going to apply to solution of differential equations. You transform the whole blamed equation and you get an algebra equation that you can solve usually using just partial fractions. And by the time you get done with the partial fractions, you end up with expressions like these, and you know what they transform back to. So you transform into Laplace space, and then you go back into your original space. And we're going to do that. First we need this. Okay, so Laplace transform of f prime of t is the integral from 0 to infinity of f prime of t e to the negative ts dt. Well, what can you do with that? Well, you can do integration by parts. If you let dv equal f prime of t dt, then v is just plain old f of t. So the e to the negative ts has the convenient aspect that you should be pretty well versed on, having done a dozen pretty decent problems where you have to do these integrals. This could be your u or your v function, okay? Or the e to the negative ts dt could be your dv. Equally well with e to the negative ts being your u function, because its derivative and its integral are both constant multiples of itself. So it's very convenient. Any such integral you have your choice here. Okay, well, we're not going to choose to let this be your v dv, because then you'd have to take the derivative of this. Your u would be f prime, so your u prime, your du, would be an f double prime of t dt, and we don't want to go in that direction. So we're going to let u equal e to the negative ts, so the du equals negative s e to the negative ts. And that's kind of the opposite of what we've done in the integrals for most of these, because we have usually let the e to the negative ts dt be the dv. Okay, dv is going to be your f prime of t dt, so the v, well, antiderivative of the derivative is the function. Okay, and that makes it really easy. So now we can write this as f of t e to the negative ts evaluated from 0 to infinity. And again, you're fresh on having done these, so you know that's your uv, evaluated, of course, at the limits, minus, and I don't want to write out this stuff, it's minus your v du, your du has a minus on it. So again, taking a big chance, because the way I've been going, you don't know, but I'm going to stick my neck out and say that's a plus s times then the integral of, write it, f of t first, e to the negative, and you got a dt on this, e to the negative ts dt. See how I keep forgetting to write things down? Now it doesn't even look like a dt here. Okay, maybe it does now. Right. Well, anyhow, there it is. When t equals 0, this is just f of 0 times 1. So you're going to have a minus f of 0, and there's a minus sign that okay, well, there it is. And then it's going to be plus s, also at infinity. Remember, there are conditions on f of t. It can't grow faster than the exponential function. It has to grow more slowly than the exponential function. And as long as that's the case, as long as f is a valid function for the Laplace transform, the limit at infinity is going to give you 0, because the e to the negative ts going to 0 much faster than f of t. It might go to infinity. Okay, so anyhow, we got this, and then we get plus s times this integral, but that integral is just the Laplace transform of f of t. Okay, that's going to be a big deal. For some reason I don't want to see that negative there. I'm going to write it down anyway. So this will be negative f of 0 plus s times the Laplace transform of f of t. And I'm going to cut the video off at this point, because I want to look and see if there's some way that I messed up the signs on this thing, or if I just am not remembering this correctly, which is likely because I don't seem to be able to remember minus signs. Yeah, that should pass in a few weeks. It's kind of universal this time of the year. You can't do much about it. Okay, so I'm just going to close this video saying look this up, make sure that should be a minus sign there, and if it isn't, get a good laugh out of whatever it is I did wrong here.